Hello, everyone. Thanks for attending this webinar. My name is Alejandro Villena. I'm a R&D researcher at KEYSIGHT. Been working with within the CENTRIC program project with Sebastian and some other partners to essentially develop a proof of concept that we're gonna talk about. Right? We named it testing and validation of 6G neural receiver, but it's essentially you'll see in a minute is a whole test bed that we developed for AI in the physical layer, essentially. So just to put in place, this is actually coming from Jacob Hoytis, from the colleague of Sebastian. I just want to put this super quick slide to know where we are. As Sebastian explained before, we are the neural receiver is trying to substitute this channel estimation, equalization, and symbol mapping, right? We just want to see this neural network. From KEYSIGHT perspective, our idea was to, okay, if we know how to test normal equipment, let's say legacy algorithms, let's scratch our heads and trying to also, now that this substitution is being made, let's try to also build a system that is able to assess the performance of these new paradigms of receivers, right? So this is a slide that I stole from Sebastian from all presentations. Essentially, what I want to talk here very quick is the methodology that the guys from NVIDIA followed for this demo. The version that we're gonna use here for the experiment is a version of the neural receiver. It's gonna say the initial versions of the project that was presented on the project. So it's not the super refined version that Sebastian was presenting at the end, but it's a good enough for this proof of concept. So essentially, we started with a pre-trained neural receiver that is being trained on stochastic channel models from pre-GPP, in this case Urban Macro, right? Which essentially is thoroughly trained, takes a few days of training, right? Pretty potent, pretty powerful, as it's been shown before. And then the idea here is to make a fine tuning. Now that we have we substituted all these legacy blocks with a neural network, we can do fine tuning, right? We can do what is also called a site-specific neural receiver, right? And for that, it was generated a ray tracing based channel was generated around the user's positions where I'm just going to play this as I speak. Random users positions were sampled around the area, right? This is the outside area of the Mobile World Congress. So the channels were computed for these random positions, and this fine tuning was actually, as Sebastian told, was actually pretty fast, right? And then at the end, what we do is we select just two close trajectories of those users, of two users, sorry, moving around a couple of buildings, right? And these trajectories are the ones that we actually, from KEYSIGHT, we're gonna receive, and we're gonna embed in our test bed to test the neural receiver, right? So in the next slide, how does the test bed looks like? Well, I'm gonna go through in details, but essentially what we're doing is trying to adapt to the this configuration that Sebastian also showed before. So it will be two users in the uplink, each user with one antenna, right? Take my pointer here. With two users, each with one antenna. It will go through our channel estimation, evaluation, sorry. At the end, we're going to receive with an ORAN network. I will go exactly into details about all of these points, right? But essentially, it's to try to replicate, to adapt to the configuration that it was shown before. 2x4, 132 PRBs, MCS 14, I think it was fixed at that point. So essentially, starting from that configuration, we build something around it, right? So again, we start by configuring in one of our software, Signal Studio or Signal Generation. We agree on these configuration parameters. Essentially, we build our signal, right, with 5G signal, which we can now download directly to the MXGs, as we call it, the radio frequency sources, essentially. Each one of those is a different user, so they have different DMRSs configuration, so they are not overlapping, but the rest is the same, right? So we're sending essentially two data streams to two PDCHs on top of each other, right? Which is they're going to be, say, overlapping. Then we take what is called a propsync, propagation simulation, if you may. It's a channel emulator that we have. That essentially we can import, as we saw before, we can import these trajectories in the shape of channel impulse responses that can advance over time, right? What you're seeing here is essentially these stops, the delays, and the complex amplitudes, complex magnitudes of these stops that are going to represent the propagation of the channel. And this is going to be done real time in the RF domain. So our two signals are going to come here. The GUI of the propsync. So we have our two users that are going to essentially converge and be received at the same time in the receiver end, which is for our 4 antennas, right? Well, each of those users are going to go through a different propagation of the channel, right? This is just super small snapshot, so you can see what kind of things are going on, right? Then, and this is the part that we see a lot of value, we took a commercial or open radio unit from a company, in this case is Lighton, but it could have been any other, right? We just happen to have a collaboration with them going on, so we use one of their products, but essentially the testbed is, say, agnostic to the equipment. But it's a commercial radio, right? It's something you can just buy out of the shelf and plug it. Connected to ODU emulator, as we call it, we lovely call it Galaxy, which essentially is only gonna control, be the brains, at least well, the brain, the conductor of the RU, right? It's gonna send these control planes and say which part of the spectrum we have to digitalize, what's the kind of the constellation. Essentially, just sending the control planes and accepting the user plane back, right? It's just going to be a controller. One of the things that we wanted to test with this is, okay, the new receiver is, as shown before, is actually very powerful. It works perfectly in simulations, but what happens when you actually take this into the real world? And for the real world, I mean real equipment, right? It's going to be far from simulations. So this is one of the key aspects, like take the NEO receiver from the cozy environment of simulations and make it face a real hardware, right? So in the middle here, as I show in the initial diagram, we're gonna have our GPU server, right? We're gonna have we're gonna essentially sniff this traffic. So the DU emulator is not processing anything; it's just controlling. We're gonna sniff this traffic, and we're gonna plug that directly into the raw IQ samples. We're going to plug that directly into the essentially a computer with a GPU and a fiber interface. But talking about these impairments, just wanted to make a quick slide because you see that this ORU, which might not be super high grade, but you expect it to work, right? It actually works. We've seen other demos within the company that uses this radio. But even if you do what is called a calibration bypass, essentially you just send a completely DMRS, not even a DMRS, just like a flat signal in the frequency domain. You see few things, right? In the amplitude, you see a kind of a ripple that is constant to this equipment. Is essentially due to the RF components and the way it's designed, right? So because it's actually constant, we change one from one equipment to the other from the same product number, let's say, and it just keeps constant, right? So that's a constant you're going to have all the time. So on top of this, you put whatever, like the DMRS is going through channels, you're going to see this ripple convolve, let's say, on top of these channels, right? You also see a phase shift from subcarrier to subcarrier, but also something even more, because this is something that can be at some point even small comparable to the actual transmission, right? To the actual magnitude of the channel. But if we look at the antennas itself, what we will expect is that, well, the power and the phases of the antennas are, well, essentially similar, right? And what we find is that they are not. So what we're seeing here is 8 plots. So it will be 1 DMRS point per antenna and per user. So we have 8 lines in each of these graphs. And what we see is that essentially the antennas, they give us different power. And this is something that changed from one unit to the other, let's say. Also, a phase disparity, a phase, they're not in phase 100% between the antennas. And more importantly, they can vary a little bit. They can jump over time, right? If the conditions are, if the temperature changes, or even if the LOs, the references of the equipments are not perfectly tied together. And actually, in this graph, we had a lab setup, right? We had the transmitters and the radio. They have been sharing the same clock. But if you don't do that, essentially, the difference between the antennas, the phase difference, they keep constant, but overall it changes, it drifts. You can see that essentially it doesn't stay as a just one line. So all of these things is something that the NEO receiver had to essentially deal with. One of the things that we also like to do as a first experiment that we've done for other proof of concepts is, okay, you train in your system, and then we evaluate in our system what is the effect of these disparities, the effect of this mismatches between the two systems, well training and well evaluating, right? So obviously there are some. I'm gonna go through that in a moment. But essentially, at the end of this, when we sniff these IQ samples and we put it in a computer with a GPU, we see that, well, the NEO receiver can receive this live data, right? Not just in a simulation, but it can literally consume real time. I'm gonna just play this video here. It's supposed to be a video. Yeah. So the lines here are pre-computer course. The video is essentially we doing the demo, pressing play, and we are live capturing this data, this stream data, which is real time, at least up until the point that it gets to the GPU, right? So we see 3 lines here. A traditional baseline, if I'm not mistaken is one of the baselines that Sebastian also showed. So kind of simple receiver. I think it's a least square channel estimation based. And then we have 2 NEO receivers, 2 versions of the NEO receiver. One that is this pre-trained one with urban backhaul with these stochastic channels, and the other one is the one that is fine-tuned with the site-specific for be a site-specific NEO receiver with data coming from the ray tracer, right? But this is being trained again in Sebastian's computer, right? And it's being transferred to us as a black box, if you may. And we are introducing the CIRs in the prop sim. So what you're seeing here is the actual the NEO receiver that never being faced with the real equipment, evaluating our real equipment, right? So one thing that we notice is, well, the gain between the site-specific and the pre-trained still exists when we use the real hardware thing. As I was informed, the gains are gap between those two is smaller than in simulations, but also this can be due to all these impairments that I just showed in the slide before, right? And also the overall, if we compare this, we put it on top of the simulation ones, the performance is worse. Again, we are taking a NEO receiver that I've seen nothing but nice channels, okay, with white Gaussian noise, right? But this is way far from white Gaussian noise. So still impressive. The NEO receiver was able to generalize pretty well to this completely unseen realm, right? So yeah, we haven't done this experiment yet, but probably if we do this calibration to the radio to calibrate these impairments that I just showed, probably the performance will go way lower, right? And similar to to the simulation environment. But it was nonetheless super interesting to see how the NEO receiver could, without prior knowledge, just face and deal with all these impairments, right? So to summarize, we have replicated this multi-user MIMO configuration with 2 users, where we have 1 antenna per user and 4 receive antennas in the receiver side. The post-FFT signal processing, so essentially the baseband processing is being done by the NEO receiver purely. So we're just feeding raw IQ data, as raw as to the point that they are extremely impaired. Well, we faced the NEO receiver with a 5GNR compliant push signal through a commercial radio unit, right? And we also showed these gains of the site-specific NEO receiver that it was proven in simulations, but we again prove it in hardware. Just to show like an abstraction of the testbed essentially that we did for setting up, etc. And just to finalize before, well, also as a dissemination. Sorry, Sebastian, for the picture. It was in LinkedIn. This is a picture of my boss Michael Dudon and Sebastian in the booth that we have from Mobile World Congress 2024. So we showcased this demo in Mobile World Congress 2024 in the KEYSIGHT World in Korea. Also kind of small conference for sales, marketing, and people and companies around the Asia area. Right? We showed it in UCNC 2024, and we're gonna showcase it with something else that I'm gonna show in the next slide. ICM LCN 2025, which is next week in Barcelona. I'm gonna be there. Me and Carles, sorry, I forgot to mention, is also being part of this demo. Carles Navarro Manchon, my colleague, right? So to finish, I just wanted to make a remark that essentially we can do some other things with these test beds, right? We took us some time to develop, to polish, to tame all the equipment involved. So now things that we can still do without changing the hardware. Well, for starters, we can train the NEO receiver. We can record a data set of this NEO receiver by controlling the payload that we're putting in the sources. So by inputting channels in the prop scene, either those are 3GPP channels, sorry, or ray tracer channels, but essentially by controlling the payload going through a channel and receiving and recording the receive slot after the radio, we are gonna have a data set. We've done it before, but we can do it in a large large quantities to have a nice data set of a real world data that can be used to train a NEO receiver. Right? We can do also do the same thing, but for a channel estimation data set. Essentially, in this part is going to be very similar, but now we're focused. We don't care about the payload. We care about the channel impulse responses. So we also done this experiment internally because essentially we have control of everything that is happening in the uplink system, right? Another use case that we did for, in this case, with Interdigital, which Ahmed, the colleague from Interdigital, is also going to present after, not about this demo, but some other demos. But essentially, we collaborated with them to do something similar. But in this case, the idea was to do a joint communications and sensing. So we're also going to use a ray tracer based channel, in this case indoors. And they very cleverly, they essentially, now our data set, our samples are going to be a human, well, simulate a human in a ray tracer, doing different stuff, right? Moving around, sitting up, standing, going in, going out. Because we have the radio, after we can extract the IQ data, we can map what was the human doing inside of this virtual world, right, with electromagnetic properties and everything. What the human was doing and what the IQ samples look like. So now we can use this to generate millions of data points, millions of samples to train an AI model, and that's exactly what Interdigital did. So just to finish, I'm going to show a super quick video of what it looks like. This is from the real data. This is coming from the in real time from the IQ samples. Essentially, we see that the AI model, but just looking at the pilots, it can estimate with an accuracy of 17 centimeters the position of the human inside of the room. It can classify the activity, whether it's walking or stationary, and it can essentially also classify the presence, right? Whether the human is in the room or not. And its bounding boxes are obviously processing, but the model is giving you the coordinates essentially and the classification. But again, just looking at the pilots, and this is being done real time, right? So yeah, this is the kind of things that the developed testbed was able to enable for us and for the partners within the project. So I believe that concludes my presentation. Thank you for attending.